Okay, here's a wrap-up of Lesson 77, Graphing Logarithmic Functions. This is a short lesson, it was a half day. A couple of notes to take on here, though. We can think of a logarithm as what kind of a function? Well, we can think of it in two ways. A logarithm is an inverse exponential function, or you could also think of it as a what power function. You could refer back to an old lesson to see what I mean by this. There's a lesson called that. Now, if you wanted to graph a function, any function, but you didn't have a calculator, how could you find points on that function? Essentially, what you could do is you could pick small values of x, like 0, 1, 2, etc. You could plug them in, and you could find y. Now, to start off this lesson, we defaulted to the calculator. We use something that I call, rather than everyone calls, the change of base formula. The change of base formula allows you to deal with logarithms that have different bases. Your calculator has two different logarithms. Your calculator has log, and your calculator has ln. Now, log has a base of 10, and ln has a base of e, which is 2.718. That's on your calculator. But it does not have log base 2. So if I want to handle this in the calculator, what I have to do is take the base and bring it down, take the subject, the x, and bring that up. This is equal to log of x, because we brought the x up, over the log of 2, the base that we brought down. So this is how I could graph this in my calculator. And I could find some points from the table. So let's do that real quick. Go to my calculator. I'm on my main screen. I hit y equals. Clear out anything that's there. I type in log of x divided by log of 2. Now I hit second graph to go to the table. And I see that in the negatives there's a whole bunch of errors. That's because this function is undefined on the half of the graph where x is negative, or apparently where x is 0 as well. The function does not exist where x is negative or 0. It's undefined over there. So what we can do is we can look at the points that we do have. 1, 0, 2, 1. I don't want to graph these decimals, so let's just pick the nice ones. 4, 2, and 8, 3. So we'll start off with those. The point 1, 0 is right here. And change my colors a little brighter. 1, 0. We have the other point was 2, 1. And then 4, 2. 4 over 2 up. And 5, 6, 7, 8 over. And 3 up. This function looks a little like this. On the left-hand side, we can look at numbers in between 0 and 1. We can plug those x values in if we wanted to, between 0 and 1, to see what happens in between there. But essentially what it has is it has an asymptote where it comes down like this, and it bends to the y-axis, and it runs alongside it, getting closer and closer, but it never touches it. That's because this line right here, the y-axis, also known as x equals 0, is the vertical asymptote. Now that you've watched me do this one, log base 2 of x, I'd like you to pause the video and do log base 3 of x. Okay, now if you're watching this, I assume that you have done so already. You've already found some points. That's my first point. At 3, I go up to 1. At 9, I go up to 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We go up to 2. So it goes up over here on the right. And on the left, remember, asymptote runs right next to the y-axis on the way down. And has this same asymptote of x equals 0, which is the y-axis. Now there are a few features of these logarithmic functions. They all have a vertical, meaning up and down, asymptote. That's an x equals something function, x equals something line. Usually it's x equals 0. Changing the asymptote would occur by a horizontal shift, meaning shifting it left or right would change the asymptote. And these functions climb slowly on the right, slower and slower the further out you go. Now I want to show you how you could find some points on this without having to use your calculator. So number 5, we know what we could do. I just did it in the first example. You move the x up, you move the 5 down, and that way you can get log of x over log of 5. And you could plug this into your calculator and look at the table to find values. But that doesn't really help us understand logarithms, so what I'd like to do instead is I would like to use our favorite, the swoop. 5 to the y equals x. So let me write that down. In the order that I passed through those characters, those terms, I got 5 to the y equals x. Now let's plug in and see if we can find some nice values that'll make us some pairs. So if I plugged in a 0 for y, I would get 5 to the 0 is equal to 1. If I raise 5 to the first power, 5 to the 1 is 5. 5 to the 2 is 25. And I think I'll stop it there. I could do 5 to the 3, but it doesn't matter. Now here's what I get. Y is the exponents, 0, 1, and 2. X are the output numbers. This is the inverse of an exponential function, so it behaves kind of opposite. So let's see, what are my points? X, comma, y, so green then orange. So 1, comma, 0, 5, comma, 1, and 25, comma, 2. These are 3 points on the graph of that function. So if you're asked to find points on the graph, not having a calculator is not a good excuse. Number 7 is interesting. We did this in class as well, because we said that log of e is what ln is actually equal to. So this is log base e of x is equal to y. When I swoop it, e to the y equals x. We plug in some values. E to the 0 equals 1. E to the 1 equals e. And e squared is equal to, well, I can't simplify that, so we'll just leave it as e squared. Same thing I did before. Y is all the exponents. And x is the outputs. So my points here would be 1, comma, 0. Hey, it's the same point from before. E, comma, 1. And e squared, comma, 2. Those are 3 points on that graph. Now let's go to one of these examples in the back. If I wanted to type number 13 into my calculator, for instance, remember the x goes up and 7 goes down. So I can write this as log of x over log of 7 plus 1 is equal to y. And I could just plug this into my calculator to graph. I'll show you how with the first one, but I'm not going to show you the answers, just how to type it in. I've got log of x, close the parentheses, divided by log of 7 plus 1. PEMDAS will handle that for you. And I could go to the graph and get some, or the table and get some values out of here. And if you have to round them, don't worry about it. I like to look for the nice even numbers, but if you can't find them, you could always pick some and just keep a couple decimal places on it. Sometimes you got to go kind of far to find a nice one, right? Like 49.3. And I also asked you to find the asymptotes of these. A regular function always has an asymptote. A regular log function always has an asymptote of x equals 0. I can even see it on my graph if I wanted to. Take a look. Does it appear to cross the x-axis? Let me hit zoom. Go to zoom in. I'll zoom in near the origin. Okay. Looks like it touches it. Let's see. Let's zoom in again. And go down to that point. Oh, dang, it doesn't touch still. Now, you can keep zooming in, scrolling down if you want, but you're going to find exactly the same thing. If you keep zooming in, it never actually touches. So x equals 0, the y-axis, that is still going to be my asymptote. X equals 0. The only one that's different is this one right here. Let me switch this to red. Number 14 was the only one that was different. A +1 on the inside is a horizontal shift of left 1 unit. So essentially what that means is my whole graph, the logarithmic function and its asymptote, would all shift 1 unit to the left. So I would instead get an asymptote that looks like this, and now we get a function that looks like this, and my asymptote would be x equals -1. That would be my asymptote because of the left shift 1 unit. You can check the table to be sure that that is indeed the case, but I'm probably right because considering that it is my question. So x equals -1 is my asymptote. And you could work on the rest of them to find values on these functions. So good luck.